Okay, good. So, yes, there was big news last Thursday. It was that Raspberry Pi announced their first new microcontroller to the world. So we've been working. Well, I've been working on it with them for a bit to port MicroPython to this chip. So that was a lot of fun and also hard to keep under wraps. But well, not hard, just wanting to tell everyone because it's very, very exciting. So I think the two exciting things are that it's a new chip. It's a pretty bold step, I think, to make a new piece of silicon because it's a very, very crowded space. Obviously, there are lots of vendors, and vendors buy up other vendors, and it's pretty cutthroat, and margins are thin, and so on. So it's a pretty hard space to get into. So it's a very interesting decision, I think, but it's very cool. It's something I think, I would love to do, to make my own chip, but I think to have the idea and then execute through and actually do it, I think is pretty amazing. And I think this chip it feels like it's designed by people who are not just hardware or not just software, but straddle the whole range and looked hard at other microcontrollers, not only the hardware, but also the SDKs and the datasheet. And what they've tried to do, Raspberry Pi, is I feel, mix those three things and get a really good balance of hardware, features that you want, really well-written datasheet, and a good SDK. So I think they've done a really good job there. And I'm really interested to see how it changes the industry if it does. If it pushes other vendors to improve their SDK, improve their data sheets, and also add cool features like PIO, which I'll talk about. So I think it's very exciting. And no, it doesn't have wireless, but you could add a wireless coprocessor. But on its own, I think it could replace a lot of standard microcontrollers that don't have wireless as sort of a workhorse chip. It's not it's not an M4 or an M7. It's a dual core M0, but it's still pretty performant for what it is, and the price point I think is really excellent. So I think it's sort of a really good replacement for pretty much anything that's just doing pushing bits and doing processing. It's got a lot of RAM, extensible flash, good peripheral support, and I think it could go a long way if people pick it up. So that's pretty exciting.
Had everyone heard the announcement? I didn't hear online. You guys, did everyone hear about this, or is it this news to you guys?
Well,
it was pretty news. So.
Yeah.
Yeah.
Okay. Yeah, right. Okay.
So yeah, I mean, a new chip, and then the other exciting thing for me and for MicroPython is that they wanted MicroPython to run sort of as a first-class citizen in this ecosystem of the Pico. So I've been working to get MicroPython, running on the Pico using their SDK, the Pico SDK, and I'll talk a little bit about that. And I guess the biggest thing probably is the Programmable I/O, which is this really interesting new feature. So you can read the datasheet. It's very nice.
Excellent.
And I just wanted to. Where is the page? Yeah. So the naming. Okay. They've got the RP2040 is the chip. The Pico is the board that it's on. So the port that we're doing for MicroPython is called the RP2 port because there'll be hopefully lots of boards that have this chip, and there'll be maybe new chips out as well. You can see the numbering scheme here, so maybe they change the core or amount of RAM or internal volatile memory. So this is just a part number, like most parts have a part number. But RP2 is the port name that we have in MicroPython. So, I won't go through, maybe just a quick summary of from the datasheet and what's in there. So it's a dual core M0 plus processor, so that's pretty interesting. It's really two symmetric cores that share the same memory, and running very fast, 133 megahertz max, although I think you can overclock it as well. But not officially, but yeah, it'll run faster than that. And quite a lot of RAM, so 264K of RAM, which is pretty impressive. And then there's no internal flash, but you add a flash chip of the size that you like, up to 16 megabytes, and then that's for your code execution. And it's pretty fast executing code from that external chip. If you want really fast interrupt response, you can put your interrupt routines in RAM. So there's a lot of RAM for that purpose. And it has USB, which is nice. ADCs, SPI, I2C, UARTs. Okay, so if I want to show you, here we go, the port, the actual board. In the flesh is the same as what it looks like in a picture. I've just got one here on breadboard, and there's a Neopixel attached because I was going to show how that works. If you get a prompt, it's sort of, it's just like any other MicroPython board. At this stage, you just have a prompt and you can do operations, help, and help modules. So help is dedicated to the Raspberry Pi Pico and what modules are installed here. So it's quite standard port. It has so implemented here. You can see pin, I2C, SPI, UART, and ADC, and also PWM and watchdog timer. So most of the peripherals there are supported, and you also have access to the second core using threading. If I can spell in the standard way. So task ID, so while true, print follow ID, and then wait for 2 seconds. See that it works. Okay, so I can run that on the second core. Start new thread task, and give it, say, that arg42. So it should print 42 and hello 42 every 2 seconds, and that's to running in the background. So I can also start the task in the foreground, say task 3. So the 42 is being printed by the second core, and hello 3 is being printed by the first core. So they're running together, and the way it's configured here is there's no global interpreter lock, so both cores can run MicroPython code simultaneously, and you just have to therefore be careful with locking if you want to share data structures. So I stopped the document. So that's good.
Damien, out of curiosity, is the _3, is that a completely new thing for MicroPython, or is that supported by other?
Normal Python is the same. It's called _thread because it has just a few primitives, like creating a thread and creating a lock.
But for MicroPython itself?
And for MicroPython, it's also _thread. So in C Python, like normal Python, you also have thread, and it's also got thread.start new thread. It's exactly the same. And yeah, but I don't think I'm answering your question. What?
No. Was it for MicroPython? Was it already there? Where other microprocessors did they have the dual core?
Yes.
Thing? Okay.
Yeah, _thread's been there for a while.
Okay.
It's on the ESP32. It's on the Unix port.
Okay.
Yeah. Yeah. So it was just a matter of enabling it in the right way here.
Yeah.
Okay, so yeah, that's quite useful. What else can I show you here? So one of the other things that was done as part of the work. was to improve the native emitter support for ARM v6m. So for Cortex M0 Plus, there was a little bit of a few bugs that had to be fixed to make the at MicroPython.native and at MicroPython.asmThumb work. So you can do inline assembly and native and Viper emitter. That's all fully working on this on the Pico. So there was there's a few patches there that had to go in. But mostly there's sort of one commit here which adds the whole port. It's about 5,000 lines and comes with some examples. The most code was in the implementation of the Programmable I/O, which I will get to soon. It uses CMake, which is natively, so when you build it, if it works, yeah, it's using CMake. So it's not CMake calling make or make calling CMake. It's just it's just CMake from start to finish. So that was also part of the effort, was to make it work with CMake natively. I might stop that or see if I can get it to go faster. So it has built-in, because of the flash, it's external flash, and part of it is used for code and part of it is used for storage, so it has a file system. And the implementation of the flash storage, which I was asked to go into a bit more detail of. So it's pretty straightforward. It's only 146 lines. Let me see what the main thing is here. So you've defined, basically you need to define the extent of the flash file system in external flash. So the start and how long it is basically the location of the file system. So that's configurable here, and that gives you a flash object. Now, sorry. So if I try and, okay, so rp2.flash. So the flash, this flash thingy is the instance of the flash that represents a block device. So I can do, I can read how big the blocks are. Sorry, there's 32 blocks, and they're each 4K each. So I can read one of them, so I've got to create a buffer of 4K, and I can do flash.read blocks. Read block 0 into the buffer, and then the buffer will contain all of the, whatever in that flash. Let's just look at the first bit of it. So yeah, it contains a little FS file system, which is indicated by that little string there. And hello P, I'm sure there must be a file in there. Somewhere. So the first thing to do is implement this flash object, which gives you a block device. And then there's the main methods are read blocks and write blocks, which read and write blocks to that flash. And what they do is, read blocks is actually very simple because it's memory mapped. Read blocks is just a mem copy of the region that you're reading. And write blocks, the write blocks implementation will do an arrays if it needs to, and then just a flash program. So this is calling into the underlying SDK to erase and write the flash. So the idea here is you've created an object, this flash object, which allows you to read and write arbitrary blocks. And you also need to implement this IOCTL method so that you can query the size, the block count, and the block size, and then explicitly do an arrays. So there's a few operations there which are important. But once you have a block device that implements these IOCTL read-write blocks and write blocks, you can then have a file system, and it's implemented in _boot. So this is the code which then mounts that block device as a file system. So we construct an instance of the block device here, and then mount it. We construct a little FS file system on this line. If that fails, then we try and format it here, and then recreate it. And then once that succeeds, mount that in the root directory. So these two files, the flash is the implementation of a block device, and this boot .py will do the rest of the work. So that gives you a file system, and that's pretty much how you can implement a file system on any board or any port. And we can even, while we're here, we can unmount the file system, and when we list now there's nothing left. If we soft preview it, it'll go back. Okay, so I'll move on now to talk about the Programmable I/O, which is the, I think, killer feature perhaps of this chip. So in my mind, the way it works, Programmable I/O, it's like a state machine or a CPLD or something, but you have 2 PIO blocks and they each have 4 state machines, so you really have 8 independent programmable state machines. They have to share memory and kind of share interrupts, but they're pretty much independent. So you can write a program, you can write 8 independent programs and run them independently on the 8 different state machines, and it will usually work. And they each have an independent interrupt, and they can access independent I/O. So these state machines are heavily tailored to turning pins on and off and reading pins with very accurate timing. So the timing of the state machines is all synchronized to each other and also synchronized to the clock of the CPU, and you can get cycle accurate counting of your the state machines when it's executing. So that's kind of the crux of it, is this cycle accurate stuff. And I'll show you an example of how one works. So the main thing is that there's this new decorator that allows you to create functions which then execute on a state machine. So it's like writing inline assembler, but you're now writing assembler for the state machine, and then that can get loaded onto the state machine. So this function here is a definition of the state machine program, and it's written in the state machine's own little assembly language. And when you execute that function, it gets turned into basically just a byte array of machine code, which can then be copied into the state machine's memory. You can inspect that actually if you want. Maybe I can show you this. When we execute this, I'll show that. So once you've defined your function, you then create a state machine. So creating state machine 0, you've got 8 state machines, 0 through 7. You pass it the program, which is this blink 1 Hertz function. You can guess what it does. And then you say the frequency of the state machine to execute at, so it's executing at 200 Hertz. And I've got the cycles here. So this first loop here, sorry, the mouse doesn't work very well. There's too much casting
So when
going
you
on.
choose frequency, do you have to then think about the clock frequency of the device to divide it correctly?
Yeah, the frequency you specify here is automatically determining the prescaler for the state machine based on the internal frequency chip of the thing. So this will be the frequency of the state machine. So every instruction takes, it can execute 2,000 instructions per second. That's what you've asked it to do. Now if you ask for 2001, it can't do that, or 2002. There's a fixed number of things, but it can do 2,000 Hertz.
So it still has to divide correctly into
certain
numbers.
It's running at 125 megahertz, I think, so it has to divide into that. There is a fractional divider. So there are certain frequencies you cannot get, but for the most part.
Prescalers, you can get them close, but never quite perfect.
Yeah, you can always adjust the routine here. I just made 2000 because it was easy to do. But so you can see this first half of this loop runs in 1,000 cycles, and the second half runs in 1,000. So it should run at 1 hertz if the thing's running at 2,000 cycles per second. And I've put some calculations here for the actual number of cycles. So this first one is 1, and the next instruction takes 1 cycle. Now the next instruction takes 6 because the instruction itself takes 1, and then this thing in brackets is the extra number of delay cycles you want that instruction to take. So this programmable I/O assembly language has this feature where every single instruction can also have up to 31 delay slots in it. So it's like every instruction is the instruction plus a delay, which is quite good. So you can make the instructions take as long as you like, or up to 31, up to 32 cycles.
So they're like just a single no-op instruction for that.
So this no up in 29 is just 30 cycles of doing nothing. Yeah. And the label itself does not cost 0. The jump costs 1. The jump costs 1. It's jumping up to this label here. So what? So you do your operation and then you delay. That's how it works. And then down here you've got the other half of the loop. So the first half turns the pin on, so that's this set pins 1, and the second half of the loop turns the pin off, whichever pin you've connected to it. So this is turning a pin on and then delaying for 32 times 30 plus 1 cycles. So we've got a count of 31, but it's actually going to do 32 because it has to get to 0. And then 30 cycles here plus 1 for the jump. So if you add up all these cycles, you get to 1,000 for that block, and the second block as well sets it off for that many cycles. So when I instantiate the state machine, I also have to tell it what pin actually to connect to that state machine. So I could connect any pin to it. It expects to be connected to 1 pin, and it will toggle that pin on and off. So I can actually create 2 or, up to 8 of these. I can create 8 instances of this program and connect them all to 8 different pins and have them blinking 1 hertz on each pin independently. Or I could change the frequency of the state machines. This has actually got an IRQ handler to make it a little bit more interesting. So every time around the loop, it also raises an IRQ for the main system to get. So the state machines themselves can raise an interrupt request, which is then signaled on this main CPU as just a normal interrupt. Rel 0 means that you can either interrupt an absolute number or relative to the state machine number. So if you instantiate state machine 7 and you do IRQ rel 0, it's actually IRQ 7 because you've got to add the state machine number to it. That's so that you can instantiate independent state machines that have different IRQs. And then the IRQ handler is just set down here. It just prints the current time. And then SM active state machine turn on, basically. So if we run this program, I'll leave that there. And so you can run these examples yourself if you have a board. So what happened? Okay, so it executed it, and now it's printing every second the current ticks, and you can see that it's cycle accurate, so it should be exactly, or plus or minus 1, but it should stay stable in terms of the state machine is interrupting the CPU at exactly the rate that the CPU itself is counting. So we're getting exactly 1 second every time here. This is in milliseconds. And also the LED on the board is flashing, which is on pin 25. Sorry, it's impossible. It's a very dull LED, but it is blinking at 1 hertz with a 50% duty cycle. So of course, I mean, this is obviously the hello world of PIO, but there's a lot of obviously things you can do with this. I will just click that and no. Yep. So the other one was pin change. So this is simple, but interesting. Basically, it's a function that just waits for a pin to go low and then raises an interrupt to the CPU. So we wait for the pin to go low, is this one. Then we interrupt, and then we wait for the pin to go high again, and then wrap back around to the top. There's a special wrap function, which loops around. So this is just a piece of code which waits for a pin and then interrupts. So it's kind of making your own pin interrupt routine. And then we've got to instantiate the state machine. We can instantiate two actually. State machine 0 here waits on pin 16, and then the same program is reused in state machine 1 to wait on pin 17. And if we run that, I've got to then be able to pin change 16 and 17. If I run my fingers along here, maybe, might take a little bit more. I think, there's a pull up, so I need a wire, but does anyone have a wire?
Sure, we can find on here somewhere.
Sorry?
I'm sure we can find on some of it.
Yeah, here's it. So it's pulled low, pull up, so I have to make it low. And who knows where 16 and 17 are. But there, so where's 16? So there's 0 and 1. So whenever I touch it, it's a little bouncing, but you can see there's an interrupt.
Maybe.
And it prints the current timestamp, and then the state machine that interrupts.
My chargers. Do you want to grab my charger? I'll grab it.
Maybe hold on a second, Dan. So we got
I'm still on. Do you see here?
you're fine. It's all the breakfast just run out of time.
Okay. Can I stop?
Yeah, thanks. Just a minute.
I think I'll tell everyone. Hello. You can. Okay, good. We're still here. We had some problems. Are we back online?
Not sure, that'll explain what's going on.
Okay.
But they can hear you through your laptop thing, so if you
I've muted myself now,
okay.
and I've muted the laptop, so that
Yeah,
doesn't.
just give us a moment, I think we'll get this one back online. Just to give you a heads up, there's a couple of questions. Sienna asked how long have you been working on this, and Scott asked about roadmap for MicroPython.
Roadmap for MicroPython.
Yeah, well, what's
All right, I'll just quickly finish off.
No,
the,
please. Yeah, just to give you a heads up, that was a question.
Okay.
Okay, we're back.
Are we back?
We're back.
Okay, so the last demo I'll do, and then I'll answer some questions, is Neopixels. So we all know that Neopixels are pretty cool, but they always require very tight timing, and then you either have to implement it with a SPI or with interrupts disabled and bit banging. So obviously a PIO is really great for this. You can do any arbitrary timing that you like, as long as you set the frequencies correctly. So here is a function which does Neopixel output, which is, you can see, is very small, so it's pretty nice. It's quite cryptic, I guess. It's using a lot of these delays in very tactical ways to make sure that it gets the right timing for the bits that are going out. And basically what it's doing, there's a lot of features here that I don't have time to explain. But with the Programmable I/O, the way you can get information in and out of it is by a FIFO buffer. So each state machine has a FIFO of 4 or 8 words deep next to the CPU. So the CPU can push data in and pull data out. And the state machine itself can block if it doesn't have any new data on the FIFO automatically. So what's happening here is the state machine will wait until the FIFO it can read from, which means the CPU's given it a new piece of data to output. And then it reads that data and goes and blits it out as the correct form for a Neopixel. And then it goes back and waits for the next pixel, the next RGB value. So each word that it reads is an RGB value that it's outputting. So this pull threshold is 24 bits, is saying exactly that. And auto pull means delay until it's got a new value on the FIFO.
So it's going to wait for at least 24 bits to arrive before it...
no, it waits for a word to be pushed, and then it will shift out 24 bits, and that 24, after it shifts out 24, it will then wait for the next word. So the 24 is specifying that after you've shifted 24 bits, you've finished with that and you need the next piece of data. The PIOs also have sort of built-in shift capability, which is like for I2C or UART or SPI or Neopixels, is that it can automatically shift out the current word on the pin that you've specified, and also shift in. And that's what it's actually doing. Hang on, out one's not next. Where's the shift? Where is the shift? Yeah, it's automatically happening in this instruction here. When you output, so X is the register that shifts automatically, and you're outputting the lowest bit of that to the pin that's specified below. Shifting it left by 1, which is specified up the top there, out shifter, shift left. And then this will go around 24 times. There's actually no counter. It's automatically done in that 24 as a pull threshold. Suffice to say, it's a pretty compact description of what's happening, and I don't really want to go into any more detail of how that works. You need to read the data sheets, but it's got a lot of very interesting features, and we need to, it's a bit cryptic sometimes how it's working. But you can see this code here is creating a state machine and running at 8 megahertz, so that's the frequency you need to get the right timing for the WS28, 12s. On pin 22, so I could instance set this on any pin I liked and then start the state machine, and it will wait for me to give it data. So I created an array of data to pass to it. Here's just some code which is making a pretty pattern. But the most important one is this SM put. So state machine put the array. So this array of words will put out onto the FIFO until it's drained, and then it will go around and do the next loop. So this is currently a blocking call, but in the future it would be good to make it a non-blocking call. And if I run this this code, it should. So let's try again. So yeah, the Neopixels are just going through this pattern, and I don't think So I think it's pretty amazing that you can write a little bit of assembly code here that can do something like that with perfect timing. And I think what the PIO is useful for is you're no longer bound to thinking about, oh, how do I use an SPI or UART in a special way to do what I want. It's like, now I can design my own protocol or interface with this strange chip very, very easily, and I'm not bound anymore by traditional interfaces like SPI. So I think it really bridges this gap for hardware and software, and it gives you much more flexibility in what you can do. So I think the PIO is pretty cool, and I think there's a lot of things that can be done. Like someone's written a DVI output driver for it already. Well, that was written not in a day, but while the project was still being made, and maybe you can write an Ethernet driver as well. But there's a lot of things you could do, I think, with these things. So it's pretty exciting. Of course, these are not original, and the BeagleBone has I haven't played with it, but has the similar state machine thing, and CPLDs, complex programmable logic devices, have been around for a long time. So it's not an original thing, but I think the way it's packaged in this chip is pretty interesting. And with this inline assembler, so PIO assembler, the idea is to make it really accessible, and you have like a 1 second turnaround for development of like hardware level bit protocols of in your project. So I think that's something that is exciting for me, and we'll see how it goes. I think I'll stop there.
Is
There's
that
lots of things.
instruction set in stone now for a while?
Yes.
Because it's in hardware.
It's in silicon, yeah.
Yeah. Okay.
It's yes. Yeah. I mean, the names are just names, but yeah, what that compiles to, I was going to show you what it compiles to. If I just print the function when I run this thing, so that's actually that's pretty small, but that's what it compiles to. It's just the machine code is
It's compact.
is actually only 4 words. These 4 words here is the machine code, because there's only 4 instructions that actually do anything: the out, the jump, and the no op. The other ones are all metadata. So it's actually extremely small, and the other numbers there are sort of configuration values. So a PIO program is pretty compact. Yeah, you have 32 words per PIO block, so and you've got 2 PIO blocks. Yeah, but yeah, I mean, read the datasheet and play with it yourself to understand more. So it's a lot to get your head around, I think, with the different things it can do. Okay, so I think there were 2 questions from the audience. One was, how long have we been working on this? I think it's maybe 8-10 months been working on this. Yeah. But not full time. Yeah, but just since we started.
Long time to keep quiet about it.
Yeah, long time to be excited and not tell anyone. Well, yeah, no, they did a good job of keeping it under wraps, I think. Because, yeah.
How many chips have they ordered? Their first batch.
How many chips have they?
Have they ordered for their first batch?
I don't know. Sorry.
A lot.
But you can see they had like at Little Bird they had like 3,000 units in stock or something. So, yeah.
And that was just a little shop in Australia.
Yeah.
Yeah. Worldwide.
120,000, Scott, thanks. Yeah. Thanks, Scott. Scott's here. There's also a CircuitPython port as well, and Scott's done, we've just been talking about it in the chat room. Scott's got an alternative compiler where it's just like compiling like a string block. So there's a different way of doing it.
Yeah, there's lots of stuff I haven't touched on. Yeah, so Adafruit are making boards, SparkFun are making boards, CircuitPython has support. That's what I know of. There's a MicroPython book explaining how to use it. You can write code in C or C++ with the SDK. Yeah, there's lots of resources that they've launched at launch, so you can dig in. Boards are already out there in people's hands, so that's cool. Yeah. Is there any more questions? I know Scott had one.
Don't think so. Gwen's... No, I don't think so. CircuitPython using the PIO ASM form, the PIO ASM tool ingests. So it's just direct.
There is the SDK itself has an assembler that you can use. you don't have to use this inline
Yeah.
stuff. But
So the difference with Scott, and Scott's library will probably port across to MicroPython, I think. But it's designed to ingest the standard PIO assembly. Whereas Damien's got like something that looks very similar but can compile down. Like, or it's
that you can
Python
write
code.
in line, yeah.
Yeah.
But it's supposed to look as similar as it could with
Yes.
the being yeah. So
It's pretty cool stuff.
I'm pretty excited. It's just another microcontroller, but I think it's
It's
exciting.
an interesting one. Yeah.
It's kind of a perfect. It's almost a dream for MicroPython because it's got a lot of RAM, and good flash and a good speed. Like it's a really good chip for MicroPython, I think.
Yeah, it's good. You touched on other chips having this stuff. That's true. Like the bigger one really interested me when that was first released, but those boards are like $100. So I think the interesting thing about this is you've got access like on a couple of dollar microcontroller. You've got access to something which has good control over timing. It's pretty exciting.
Yeah.
There are some weird things like the floating point support is a little odd because it's in software but on silicon, because M0s don't have floating point support. So what else is?
Yeah, it has single and double, but
Yeah.
single is a bit faster because it's shorter.
Yeah.
It's easier, faster to compute, but it does have double precision if you enable it.
What's left on the Pico port?
Yeah,
or
good
the-
question. So power management, light sleeping and deep sleeping, and RTC wake up. That's kind of the main outstanding thing. Being able to set the RTC, still outstanding. And then I think there was a few things in the PIO. There was a few sort of esoteric things, not esoteric, but sort of final things that haven't been supported yet to add. And then asynchronous stuff. So making asynchronous SPI, asynchronous PIO, putting and getting. I think that will go a long way to make it integrate well with async IO. So you can tell the PIO to constantly output this buffer, frame buffer, for example, while you do other things. But yeah, most of the features that think it's supported, like there's a good PWM block and ADC is quite straightforward. Pins, the I2C, SPI and UART are all standard. So, and then I think, threading and multi-threading needs a bit more testing and making sure that it doesn't have contention. But that's all the tests pass. And I think most stuff's there. There's still a lot of USB that can be done, like USB HID, USB host, USB mass storage, and then a lot of other cool features you can implement with the PIO, like video output. But I think that will come as a second layer that we do.
Scott's also mentioned that they've given some thought to the memory layout, and I remember that triggered a thought that they've got documentation about having 6 banks of memory and to allow that to parallelize some of the DMA.
Yeah,
Okay.
I don't know if I have much to say about that.
Cool.
I just treated the memory as a big blob, but we do use DMA in the SPI, and I think in the PIO, but it's not really exposed to the user. Yeah, at
I
this
was wondering
stage.
if the user had to configure those banks
No,
or choose what.
it's just yeah.
With the PIO being somewhat separate, is there capability to put the main processes to sleep and have the PIO running applications?
I'm not sure if you can do that. Yeah, the PIO can wake the main processor.
Yeah.
It's got an interrupt, but I'm not sure.
Yeah.
But that would be interesting.
Yeah, good for low power applications.
Yeah.
actually.
To drive the main processor to sleep.
Do something small, like periodically while the main processor is sleeping and wake it up, say if a certain amount of data has come in, or checking I2C flags until something happens and waking on that.
You'd have to do that.
Yeah. I'm not sure if the PIOs are tied to the CPU being active or not.
I always got.
Someone said that.
CPU can wait for interrupt and the PIO can send the IQ.
Yeah.
It's,
But the PIO is tied to the CPU clock, so it just depends on the clock tree if they're
yeah.
independent. Like if the CPU can have its clock gated while the PIO is still run, I'm not sure. Yeah.
Does anyone else have any questions there?
I think what Scott was asking about.
It's
Yeah.
not Pico related. Anything else Raspberry Pi or RP2040 related, or is that enough for now? Because there's a lot to absorb. I've got a few boards here as well, so if you want to play with one tonight, feel free. Cool. Well, Scott's question.
Okay. All right. So Scott's had a question. Roadmap. What is it? Roadmap for MicroPython this year or no? Well.
Just generally where MicroPython's headed is where you're
Yeah. Yeah. Good question. Well, it's.
Should we turn the recording off?
Yes, no, it's okay. I mean, this
week, this month, this year, this day.
Yeah, I think the first part of this year, I'd really like to concentrate on consolidating lots of stuff, cleaning things up that are outstanding, and cleaning up a lot of the GitHub issues and pull requests. Last year was pretty crazy. There was a lot of stuff going on, and yeah, there was. I mean, just not enough time to do everything. But because of GitHub sponsorship money, which I hope to be able to use to get some people on board to help with things like cleaning up and improving wiki and forum and libraries and things, I think that will go a long way to help the ecosystem. And yeah, it's really great to have the funding. So we have about $1,500 a month funding, which is really good. Australian dollars, and yeah, we'll put that to good use and let people know about it. So I would really like to do a lot of tidying things up and consolidating, and then there's just a lot of new chips that keep coming out, like the STM LoRa part, and yeah, I mean, the ESP, the whole new range of ESP32s with the S2 and the S4, whatever they are. We still have to get on top of those. So there's a lot of, I mean, there's just with all the things that are already there's a lot of stuff to do, and it would be nice to do the things that keep cropping up, people keep asking about. So in terms of features, I think we've got a lot of features, and I don't really want to keep adding things when other things are not. Well, there's still a lot of stuff to tidy up. So Bluetooth support is really solid. There's a lot of work being done on that, and I think LoRa would probably be the next thing to look at in terms of wireless. So yeah, I would look out for that. But I think that's my answer. But yeah, I mean, open to, well, yeah, everyone has a good opinion on what to do, but always open to suggestions about what's important. It's always good to get feedback.
So Sean's asking about Bluetooth on ESP32, like what's the ETA on that? But it's already mostly there.
Well, Bluetooth, yeah, it should be working. It's just
L2 cap's the only thing I believe is
L2 cap, okay, yeah. We need to move to the IDF4 to do that, and then it should work. And we need to get CMake working, which is very, very close. Yeah, there's just a few blocks that have to fall into place. And, merging Joanna's docs was sort of the thing that I was concentrating on, and then we can move on to those other things. But yeah, L2 cap on ESP32 will come soon, as soon as CMake and IDF4, which, yeah, there are pull requests for there, and I just have to get to them.
So on Scott's radar involves having separate support for all of the new RP2040 boards.
So
There's a bunch of RP2040 boards, so CircuitPython's going to try and cover as many of those as we can. We'll probably need to have board definitions for those too.
Yeah. Yeah, definitely we'll have board definitions for any RP2 boards that are out there.
And Glenn's just reminded me of what I was about to ask, which is about the regular release cycle.
Yeah, I know. It would be good if I actually stuck to that regular release cycle. Yeah, I really wanted to do a release before Christmas because that's when I said I would. It was even earlier than that, and then we had a holiday, so it was it didn't happen. And then the Raspberry Pi launch came, and it was something I wanted to do this week, and I maybe still be able to do it by Friday. But sticking to a regular release cycle is definitely
a goal
on my radar, on my note, like at the top of my list of things that I want to do. So yes.
Well, let's wrap it up there, shall we?
Okay. Yep. I think I've said enough.
Thanks, Damien. Thanks for the call. Thanks for all the work for that.
It's good. It's really exciting. Thanks. Well, let's see what happens.
There's people clapping.
Okay. Well, thanks everyone for being online. If you can still hear me, good to have an extended audience.
Cool. Thank you.